audio ready to go and get the chat up.
Okay.
Hey, everybody. We should be live. We did it. We're live.
Okay. That is exciting. I'm just going to keep enjoying
the
being
warmth.
almost warm.
No one can see the. Let me shift to you so people can see you with your warmth.
I am totally like sitting directly in the beam of a heater right now.
I get to hi to a bunch of
gotta
people. Hello to Arnold Post, Brooke Mulligata, Coffee Dog, Coalfire, Colin Jones, Eric Knapp, Erstwhile Notions, Gordon Dewis, Graham W., Guido Bibra, Harry M., Harry Patrick, James Aberson, Janelle Duncan, Jason Elric, Jim Becker, John Drake, John Seffield, Kevin Ayers, Mr. Tom Harbin, R. Instro, Rick Schwartz, Susie Murph, Torty Godwa, Umu, and Zapfan. Hey, everybody. Welcome to this absolutely regular episode of Astronomy Cast. How did it all go with CosmoQuest? We've reached the end of our fundraising period.
We raised about $35,000, which is enough to keep us going very part-time for about 3 months. And given the current government shutdown, we can't apply for new funding anywhere.
Oh, the irony. Oh, and I know like the AAS is going to be a ghost town.
Yeah. They're estimating several hundred people won't be able to attend due to the government shutdown. People who already paid their registration fees, probably already bought their airplane tickets, reserved their hotel rooms. Yeah.
Some people jumped in the last minute. Richard Hayes, Eric Knapp, Linda Sadiq, John Drake, Side MT, Enoch, Batman. Cool, Batman's here.
Always be yourself unless you can be Batman, then be Batman.
Then be Batman. Yeah, this is a disaster right now. I know hundreds of thousands of federal employees are not
800,000
are work
0.8
right.
million people.
Right, but several hundred thousand are working without salaries. So
yes,
800,000 are not getting salaries, but a few 100,000 are still required to work and not get a salary.
Which just hurts. And all federal pay raises are being denied in 2019. So the standard cost of living adjustments that are made and the standard regional cost of living adjustments that are made in order to just keep how much you're getting paid essentially the same with interest rates from year to year, those are being denied across the boards for everyone in the US except the military. And Trump just finished giving a speech in which he said he'd keep the government shut down for years if he had to.
But now you aren't as tightly constricted over the things you can and can't say anymore, right?
No, I can say whatever the fuck I feel like.
Okay, good. Welcome to a fully operational, unleashed Pamela. I think we will all appreciate your candor moving into 2019. Well, let's get on with this week's episode.
Okay.
For those of you who are wondering what it is that you have stumbled into, this is going to be a live episode of Astronomy Cast. We will take, I don't know, however many minutes I decide it takes for the episode to be over, and then we'll stick around and we will answer your questions about space and or astronomy. Okay, let me know when you're ready to press record.
I am ready to press record.
I have also pressed record, and now we say hi to Susie.
Hi, Susie. Whoa, I have to speak. What the hell just happened?
Some kind of echo? What was going on there?
I apparently had monitoring turned on, and it was monitoring through my external speakers,
That
and
was
that was
that was the thing.
horrific. Okay, I'm
Want me
starting
to try
over
again?
because I like Susie. Yeah.
All right. Hi, Susie.
Hi, Susie.
You missed the. Well, I guess you're watching the show live, so you missed. You didn't miss anything. You know exactly what happened. All right. Let's get on with the intro. Here we go. Astronomy Cast, episode 512, Direct Imaging of Exoplanets. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser, Cain, publisher of Universe Today. With me, as always, Dr. Pamela, senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. How are you doing?
I'm doing great. First episode that we are recording in the new year, 2019. It feels like only a marginal dumpster fire so far. Uh, should be a good year.
That's optimistic.
there's a, as we mentioned last week, there's a ton of really fascinating space science, astronomical stuff that's going to be happening this year. Everything else is irrelevant to us. All we care about is space, space, space. And that is not
Keep
true.
it simply science. It's
Keep
the
it
other
simply,
KISS principle.
keep it, yeah, exactly. Keep it simply space. Not even full science. That will, there's too much chance of things going awry. Cool. Well, how did the fundraising with CosmoQuest go? Where are we at?
So by December 31st, we're still waiting for the final numbers to come in, but it looks like we brought in $35,000. This
Wow.
is really impressive given that we started the fundraiser the day after the US government shutdown, which means that there's a whole lot of people out there who really care about our show who don't know when their next paycheck is going
Yeah.
to be. It's super impressive because the Dow Jones collapsed that day as well. And so I'm really proud of how many people that in these super turbulent times said, helping this science project, helping people better do learn astronomy and space science matters to me. And I'm going to put my wallet where my mouth is. And thank you to everyone who showed you want us to keep going. And I just hope we can make you proud.
Yeah. Yeah, thank you so much, everybody who contributed. Pamela's got some runway to run CosmoQuest for the next few months, and hopefully we can get to a point that we've got more funds coming in from some of the grants and such, and we'll just keep on doing science. Especially now that Osiris Rex is at Bennu, and that little spacecraft's going to need some help choosing a rock. So
any day now, we're going to be getting that first mosaic, and I can't wait.
Yeah, that's going to be exciting. All right. Finding planets is old news, but we now know of thousands and thousands of them. But the terrible irony is that we can only see a fraction of the planets out there using the traditional methods of radial velocity and transits. But the new telescopes will take things to the next level and image the planets directly. All right, Pamela, so today we're going to be talking about direct imaging planets. Before we get into direct imaging, let's just go back a bit and talk about the traditional ways of finding planets orbiting other stars.
Well,
the old school way, the way our grandparents used to do it.
The initial way that people found planets was they looked for the Doppler shifting of regular everyday stars by hot Jupiters. And because the gravitational pull of a planet will indeed yank around its sun, we measure those motions the same way a police officer measures if you're speeding or not, by seeing how light coming from the star gets shifted redwards or bluewards in its motion. Now, this was good in 1995, 98, early 2000s. But it was quickly realized that you can actually see the dip in light from a star when a planet passes in front of it. This was initially done mostly with stars that we knew had planets going around and around them. And after people with like 4-inch driveway telescopes started being able to replicate planet results, Well, we launched this little spacecraft that just might have been called Kepler, and we started pulling in planets 1,000 at a time, potential planets 1,000 at a time. And since then, we've been going through confirming them using the Doppler technique. And sometimes even, well, lately we've found a tiny, tiny handful of planets by looking directly for them.
All right. So before we get into the direct imaging, you mentioned that amateurs with 4-inch telescopes in their driveway can confirm exoplanets. So if you've got a small telescope and you've got like a CCD camera attached to your telescope, or you've got a DSLR attached to the telescope, then you can do this yourself. You can take the exoplanet catalog that exists right now. You can find out when a planet is going to be transiting in front of its star. You can make observational measurements of the star over several nights and measure the amount of light that's coming from the star, and you can detect a noticeable dip in the amount of light that's coming from that star. You can replicate, you can confirm that there is a planet orbiting that star. And it's amazing to me that we didn't know this 20, 30, 40 years ago. Like, this is a thing we could have done if we had sort of just known what to do. And I guess if the CCDs were good enough, is that
they weren't.
yeah.
I mean, this is the thing. This isn't something you can do with glass plate photometry. The time that it takes to expose the glass, measure the light, the errors in it, can't do it that way. So you needed to have the invention of the CCD. The early CCDs didn't have the precision, the quantum efficiency. We're looking for tiny, tiny, tiny dips, sometimes just 0.1% of light in the light from a star. And this is something we've only been able to do for the past couple of decades.
All right, so let's talk about the downside of both the radial velocity and the transit method, which is, of course, alignment.
Yeah. So with the radial velocity method, I'm sorry, my dogs have figured out how to open doors. Let me say that again. With the radial velocity method, we are limited to finding planets that are moving towards us and away from us in the plane of the sky. This means ideally we can only find things that, first of all, are big enough to yank their star around. And second of all, are close enough that they're big enough has an effect. And you have to have the geometry where they're moving in and out towards and away from us in the plane of the sky. Okay, so that's all annoying and limits what we're able to see. Now, with the transit method, it gets even worse. With the transit method, we have to have the planet precisely aligned so that it passes in front of its star, eclipsing some of the light from the star relative to us, which means the alignment has to be not just in and out of the sky, but precisely so that it's not tilted up or down too much. Even in our own solar system, we don't see Venus and Mercury regularly eclipsing our sun. If we only catch Venus every few generations having a pair of transits, how much rarer is it going to be to see alien planets transiting their stars? Well, it turns out it's pretty common.
Yeah.
But it still limits what we can see.
And so what percentage of the planets out there actually line up so we can see them?
Well, that would require me to know how many stars have planets.
Right, but I mean, if assuming a star has a planet, what are the chances that it's going to be lined up in a way that we can actually detect it using, say, even just the transit method? Like, are we talking tens of percentage? Like a couple of percent, a half a percent?
It's a few percent.
A few percent at the most.
It depends on how far away it is. It's even going to be harder to find the ones that are further out. But yeah, it's a few percent.
Right. So for every one planet that we can see, there are 50 to 100 planets that we can't see because they just don't happen to be lined up and everything is random. That sucks. All right, let's get on to the direct imaging method then. What are we doing here?
So, with the direct imaging method, we are saying we don't care what the star is doing. We don't care about the alignment between the planet and the star. In fact, that star is our enemy. We're going to do everything we can to ignore its light and strictly look directly at the light reflecting off of that planet or the light being emitted by the planet. This is often done in the infrared, where worlds like Jupiter sometimes give off more light than they take in from their sun. So we often use what are called coronagraphs to block out the light from the star. This was most famously done with the star Fomalhaut, which any of you who are correctly located on the planet are able to go out and see. And with this little world, they blocked out the central star and then imaged the dust disk around it, saw eddies in the dust disk, and used mathematics to predict where in that mess the planet should be located. And over a period of years, watched that planet systematically orbit around Fomalhaut. And if it wasn't for the fact that we've seen the sucker move, it just looks like another flicker in the dust disk. These things are really tiny because they're so far away.
And so this idea of this coronagraph, I mean, one does not just simply block the light from a star. Why is this so complicated? Right?
Well, it gets differently complicated with different systems. The primary issue is you have sunlight coming in from, or I guess starlight coming in a wave. You can't just stand in one place on the planet and go, okay, here I see the star, and then step to the left, and here I can't see the star. No, that star is giving off light in a perfect sphere in all directions. Occasionally, gravity bends that sphere hither and yon, but in general, the starlight is coming in all directions. So you have to figure out how to block all possible paths into the telescope for that light without blocking anything else.
And how do they do that?
Well, it depends on the telescope. My favorite example of a coronagraph is the one that is being developed potentially to fly with the W-1 spacecraft. This is a telescope that it turns out the military had
Yeah,
essentially in a box waiting to be launched.
right. Yeah,
And
we tell the story
because
every now and then, right? This Hubble class telescope that the Air Force used, or the National Reconnaissance Office would have used for Earth observation, but it wasn't good enough anymore. So they were just like, they said, hey, NASA, do you want this? Maybe? Otherwise, we're just going to throw it
and
out because it's garbage for what we
and
can
the
do.
annoying thing is they had two and we could only afford one.
Yeah, I'll take the other one.
Yeah, yeah. So we're in the process of hopefully, assuming the government opens back up again, of building W-1. And one of its accompanying, I don't know if the right word is instrument facilities, the thing that is hopefully going to get built to fly alongside it is a massive sunflower shaped coronagraph that is essentially a solid disc surrounded by petals. These things come in a variety of different designs. They all look like something that would be out of a James Bond movie used to kill somebody, uh, throwing stars, whatever analogy you feel like. It's that combination of different edges that works to build interference patterns in just the right way to block out the star and allow you to potentially see whatever planets may be around the star.
And these, I know this star shade is going to fly like 10,000 kilometers away from the telescope, and perfectly position itself to have the center part block the star, and then you'll have the petals sort of gathering up some of that additional light that's pouring out, and any planets in theory are going to be seen around it. But even I don't know if you've like researched into coronagraphs much. There's another way that's really interesting. The way with some of the Earth-based ones and some of the space-based ones will work. The coronagraph is built into the spacecraft or into the telescope,
Yes.
and uses destructive interference of the light, so that it takes the light, breaks it up, makes the light fight itself, so that you actually, you get the block of, you still have a disk that blocks the sun, but then you also have using destructive interference of the light to clean up all of it. And these will work best in space, but they still work okay in the atmosphere. And there's a tremendous instrument that's attached onto the European Southern Observatory. They have the the
Very Large
espresso.
Telescope and Keck
Yeah.
both have these instruments.
Yeah, these coronagraphs. I think espresso is the one that's on the VLT.
I think so.
Yeah, and so you were saying that these work better in infrared than visible.
And the issue that makes infrared better than visible light is the wavelengths are just a little bit longer, and that difference in size in the wavelength of the light is in a lot of ways easier to deal with. Now, that's not the only thing. The other thing is stars give off less light in the infrared. It's below the peak in their relationship between color and how much light output they have. And it's in the maximum light for a planet. So planets are warm objects. They're not hot, they're not stars. So we're starting to get in the infrared towards the peak temperature or the peak wavelength corresponding to temperature that a planet gives off its light. And we're getting below the peak wavelength for a star. So this also helps. We're just looking in a different color and we're getting a myriad of bonus features. And sometimes that's all it takes is just those extra bonus features the universe gives you for free if you just shift out of what the eyeball can see.
And one of the things also that the espresso instrument is able to do on the Very Large Telescope is it's able to detect the polarization of the light. And so you'll get the light coming off the star. It's going to be bouncing off of the planet's atmosphere and possibly oceans and things, and it polarizes the light and changes it into a different into a different alignment. And then the instrument can throw away everything that is not that exact kind of polarized light, so that you can only see the movement of that planet, which is essentially this tiny little polarization spot moving around. And I know earlier this summer, again, the European Southern Observatory detected a newly forming planet for the first time using this technique.
And the thing that is so frustrating is many of the objects that we're saying are direct detections of planets are being found around brown dwarfs, are being found around red dwarfs, are not necessarily planets themselves, because they might be brown dwarfs. So many of these discoveries, many of these current direct detections have asterisks next to them, just because we're not entirely sure which side of the planet star line we're on. And to remind everyone, a brown dwarf is a object that is massive enough that it may have been able to burn tritium in its core, but it only had temporary nuclear fusion going on inside the star. And it's that temporary nature that it doesn't actually start hydrogen burning that leads us to it's not a planet, it's not a star, it's its own brown dwarf kind of thing. Now, do you call something that's orbiting a brown dwarf a planet? Sure, why not? But do you call it a direct detection of an exoplanet? Or do you call it the direct detection of a rock around a thing that isn't a star? So you put an asterisk. And then there's all of the stars that have many Jupiter mass objects being detected at fairly significant distances away from the star. And the question is, are these things that are super Jupiters, are these things that are brown dwarfs? What the heck do you call them? So with our present day direct detections, there's an asterisk left and right.
So here we are now. I mean, I think we are in the phase where people are producing these first images. They're showing what is possible with the low-hanging fruit, Fomalhaut, which is the star and the way the planet work. It's sort of the perfect contrast. What is in the works then to take this whole plan to the next level? You mentioned the star shade, which is one idea. What are some of the other, what's in the works that's going to allow us to take this to the next level?
Well, I think that what was done with Fomalhaut is potentially going to start giving us a new way to look for planets. This is research that matches in beautifully with a lot of what we see coming out of the Atacama Large Millimeter Array, where day after day, we're seeing new images of protoplanetary disks with planets in the process of forming. But in these radio wavelengths, we aren't able to see the planets. By coupling the Atacama Large Millimeter Array observations with future VLT ground-based observations that allow us to take advantage of the infrared, take advantage of the technologies like Espresso, we're going to have a new way to find specific kinds of planets that have already shown us where they are by how they gravitationally ink around the disks they're in. Now, finding the isolated planets, that's going to be more complicated. And this is where we have to keep looking to the future spacecraft that maybe, please give us terrestrial planet finder. We've been begging for 13 years now. We really are going to have to wait for the space-based missions like WFIRST to get off the ground, both figuratively and literally.
Right. WFIRST. I mean, James Webb would probably be able to do it if it was connected with the starshade. The great thing about this idea of the starshade is it can work for multiple spacecraft. Many can use it, but the downside is you've got to get this alignment at 10,000 kilometers. You've got the spacecraft, you've got the starshade. You only get to look at what is perfectly behind the starshade from the position of the spacecraft. Get multiple spacecraft, and now they're all using the same starshade, but the way the lines are coming, they're looking at different targets. So that's effective. I did a video.
You're limited with the starshade on how long you can use them for, because they do have this in a single observation, because they do have this great separation between them, which means that they're going to be orbiting at very different velocities. And you're limited on the diversity of orbits your telescopes can be in, because you have to be able to get into similar enough orbits. So a starshade designed for WFIRST orbiting the Earth in whatever orbit they put it in won't work for James Webb Space Telescope. So while you can share things, you can only share so far. And I've apparently got to capture a puppy. I'm so sorry, everyone.
Welcome to watching us record this live. Susie, you may want to write down around 22:45. There's going to be some editing required. Oh.
We're doing a timeout so she doesn't learn to bark the way Eddie does.
Right. Good luck with that. He's teaching her his best tricks.
Yeah.
So I mean, one of the things that we've mentioned in the past is that there's a few technologies in addition, like adaptive optics, which allow these ground-based telescopes to take even better pictures now than the best space-based pictures that we've seen. And you mentioned that idea of the Very Large Array. There was just this amazing picture that came out about maybe 2 weeks ago, where there was a bunch of 20 different protoplanetary disks captured by the VLA, and you see them in all different, face on.
That was Alma.
Yeah, face on, a little off to the side, right? Like all the different variations you would want to see in other star systems. Now suddenly you're seeing them at every angle, and so
and every stage in their formation, from being a fairly solid disk to having progressively more and more complex planet systems around them. We're slowly building up a film, one system at one age at a time, of what it looks like for a planetary system to grow up.
Yeah.
And this is truly amazing. It's going to be finding the senior solar systems that no longer have those massive disks around them to gravitationally point us to exactly where around the star to look for that faint little planet. That's where we're going to have our
Yeah,
troubles.
but the next class of telescopes that are in the works across the board, this is going to be the kind of thing they're going to be attempting to do. You've got the extremely large telescope, which is the one that's being developed for the European Southern Observatory. This is a 39-meter telescope. When you compare it to the four 8.4-meter telescopes with the very large telescope, you've got you've got the Magellan telescope, you've got the 30-meter telescope, which is 30 meters. And then you've got some of the space-based telescopes, James Webb, and then what comes after that. And this direct imaging of exoplanets is going to be one of the capabilities that's being baked into all of them. That this is the way. Once we've got things like TESS and Corot and Kepler and Cheops finding all of the nearby transiting planets, then it's time to move to a system that lets us see them all.
And with Gaia and its extraordinarily precise astrometry, we have yet one more way to find planets, and that's by seeing how they yank around their stars in the plane of the sky. So it's not that the star is coming towards us in a way and we can measure the Doppler shifts. It's that it's actually moving
Right,
around relative
spiraling.
to other objects.
Yeah, yeah. You could see
And the
the star doing like a little wave in the sky as its planet is pulling it around.
and this is something that is entirely new, something that we've been trying to do, hoping to do with objects like Bernard's star for decades. But we're finally able to do it thanks to the amazing high resolution, high quantum efficiency systems that we have on orbit now.
Yeah, uh, and so that will serve as a great finder scope for these follow-on direct observations, because you're going to know all of the nearby planets that are going to be easy to observe thanks to the Gaia data. So they all just build on top of each other. But it's amazing to think that in, say, another 10 years or so, 15 years, that the main way that we look at planets now is going to be doing these direct observations. We will have pulled away all the low-hanging fruit of the radial velocity and the transits, and then we're just going to start taking pictures of planets. What will it take, though, to give us that picture of like another planet, like to see mountains and oceans and continents and things like that? What's that going to take?
A generation starship and waiting a few years for the signal to get back once they get there?
Right. So we're going to need to send breakthrough star shots off to other star systems before we can actually see what they're going to look like up close. The one idea is this idea of using the light from the sun as using the gravity of the sun as a gravitational lens. The only challenge you got to do is get your spacecraft out to about 1,000 astronomical units from the sun, and then you can take a picture of other star systems. But then it's amazing. Like you get to see them. Then you do get to see mountains and for whatever
It,
happens to be perfectly lined up behind the sun.
and it's that trick of getting it perfectly lined up, because if you aren't perfectly lined up, you end up with a streak, a smear, a smiley face. There's so many shapes you can get that aren't perfect. So I don't like funhouse mirror worlds. Let's just go there instead.
Oh, I say we just do both.
Okay.
All right. Thanks, Pamela. Thanks,
Thank
everyone.
you.
And we'll talk to you next week.
Okay, I'm going to pause this. Oh, there's so much gardening going on outside today, and my dogs are just,
Oh, they're
I
excited
know,
about everything that's going on.
they want to go bark at the leaf blower.
Can you blame them?
Yes,
Man,
clearly.
hate leaf blowers. I would bark at a leaf blower. Okay, I'm going to save as well. What?
So this is
512.
512.
Yeah. dog. Why don't you just go let her attack one gardener with a leaf blower?
No,
Like,
no, she may not have the leaf blower.
Nicholas B is saying that your dog is setting off his dog. Soon the whole
Oh,
world's dogs will be
oh,
whining.
hi, 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 ow.
Um,
Okay, hold on. Trying to figure this out.
all right, John Suffield
Yeah,
says by the time James Webb
no,
launches, we will
if I
have a
set you
thriving
down,
colony
you're
on
just gonna
Mars,
scratch up the
and
door, but we're gonna do that.
we'll be preparing to test the first warp drive powered starship.
Okay, let's see what happens now.
Did you catch that? No.
What
Oh, I
what
said
was
by the
that?
time James Webb launches, this comes from John Suffield, we'll already have a thriving colony on Mars and be preparing to test the first warp drive powered starship. Yeah.
Yeah.
No way. James Webb's going to launch 2021. We're just 2 short years away from its launch, and nobody can tell me differently. And I'm not I'm not listening. Arjun asks, could we directly image large exomoons of large exoplanets, maybe by noticing dips in radiance in the planet?
Say that again?
Can we find large exomoons?
Yes, but the better way to find them is with gravitational lensing.
Right.
It's just hard to predict when that might occur.
Yeah. So, so right now, again, with a small 4-inch telescope, you can detect planets orbiting other stars through gravitational microlensing when things happen to line up, and they think that they've detected occasional double dips where the planet's moon participates in the alignment as well, and you get sort of the perfect alignment. Arjun also asks, have we detected an exo-Kuiper belt or Oort cloud?
Yes.
Not
Oort
Oort
cloud, no,
cloud.
because those are spherical.
Yeah.
But with the Atacama Large Millimeter Array data, we see systems that have massive rings of material, some of which are parallel locations to where we see the Kuiper belt and the asteroid belt, and just about everywhere in between.
Yeah. Brooke Mulligata says, say something please about China's moonlander.
It landed.
Yeah.
It's awesome. I'm waiting for the photos of it from its own rover. This is one of
have
the
you seen the
cool
pictures
things
of the
they
rover? It
do.
deployed the rover.
Oh, okay. So I haven't seen them yet.
Yeah, I'll show you a
They're in the
picture.
wilds.
Yeah.
I have to admit, I got sidetracked by the funniest hashtag ever this morning. There is a Japanese hashtag that I don't have any idea how to pronounce because it was all symbols I don't understand. There was a Japanese monk who was pulled over and given a ticket for riding in his robes. And the reason was they said the robes were far too cumbersome for him to be able to drive. And this has led to a bunch of Japanese monks doing everything from fighting with lightsabers to doing amazing drum solos to gymnastics, all wearing their robes. So somehow, instead of going down the space rabbit hole, I went down the monk rabbit hole.
So here you go. So if you can see that picture.
That's cool.
Yeah.
Now that was a picture of the rover. I'm waiting for the rover to rove off and get that long look back shot.
Yeah, we don't have a picture that the rover has taken of the lander yet. We just have a picture of the rover taken by the lander. So we're halfway there. But I'm sure we'll get that shot once it's set up. So cool. William Van de Beek says that Professor Kipling has almost discovered an exomoon. Yeah, that's right. David Kipling from Columbia, Kipping from Columbia is sort of the exomoon guy, and he did a paper a few months ago that he's pretty sure they've found an exomoon. So
that's cool.
Let's see. John Suffield says the LSST is the Launching Sometimes Space Telescope. No, it's a ground telescope. So like the Launching Sometimes Surface Telescope. Larry Beckham asked, back to the brown dwarf question, where does a brown dwarf get the tritium with a half-life of only 12.32 years? Does tritium only have a short half-life?
I didn't think so.
When you stick things under enormous pressure, does their half-life change? Like when they're in the middle of a star?
No.
No? Larry Beckham is asking why the moon is so brown in the Chinese picture. Sepia tone? I mean, yeah. I mean, it is absolutely, they are tweaking the color for whatever shows the best, whatever they're looking to see, and they're gonna change the color of the they're gonna mess with the palette to be able to reveal the details that they want to see. That's interesting to them. Somebody later on can come along and turn this into what it would look like if it was your eyeballs. But remember that when you're seeing stuff in space, you're rarely seeing what your eyeballs would actually see.
And I don't know the answer to the tritium question. I now know it does have a half-life of 12.34 years.
Zapfan is saying, is it deuterium burning in brown dwarfs? Not tritium? Because it is deuterium burning as well. I think they do both.
They do both. Some only burn tritium. Some burn both tritium and deuterium. Those are the more massive ones. I'm wondering if it's just there's so much tritium that not all of it is half-lifed away. I will need to look this up. Why don't we do our next episode on what makes a brown dwarf?
We have done an episode on brown dwarfs.
But we didn't do it on their burning mechanisms.
Well, we could do a thing on the different kinds of fusion, different kinds of stellar fusion. And talk about the proton, the something cycle, the CNO cycle, this is going to get in the weeds. Let me see. We've done an episode on fusion, but we haven't done specifically the different kinds of fusion that stars do. So stellar fusion,
okay.
Sure.
Okay.
There you go. You stumped her, Larry, and now you get an episode where she's going to do the research. It's so rare. That just doesn't happen. Because you know everything,
I just
Pamela.
never thought that one through.
Well, someone asked me this question as well, which was neutrinos have an incredibly short, like 10-minute half-life. So
but they're traveling so fast that in our perspective, they live a lot longer. That one I know.
Yeah, so they're traveling at such huge relativistic velocities that for them, they only experience a few seconds while they actually are traveling thousands of light years, which is an amazing idea. And you mentioned, this before, that the Cherenkov radiation, right? This idea that these particles are making it through the atmosphere farther than they should because they're not experiencing as much time as they think they are.
Exactly.
Or as we think they are, as we experience them do. Arjun asks, why are the Chinese trying to learn something, or are they scouting for somewhere for people to land? What's the plan?
A little of both. Where they landed is a crater that is part of the South Aitken Basin on the moon. It's on the far side, which means they had to launch a relay satellite for communications as well. We don't really know that much about this side of the moon. They're going to bring some rocks back so that we can start to look at the compositional differences. It's going to help us start to understand things like, are we right about how the moon formed, and that the reason the back looks so different from the front is it was splitted upon by another object. So there's also the chance that They're going to be able to start to see revealed bedrock on that side. So there's a whole lot of scientific reasons to go, but ultimately the Chinese are hoping to set up both their own space station and a manned moon base in the not too distant future. It is quite likely that the next humans to walk on the moon are going to be Chinese astronauts.
Yeah, it is
You
most.
sound so sad.
Well, no. I mean, the thing is like anyone, if anyone can walk on the moon, then that's awesome, right? And we should celebrate anybody pulling this off. Um,
Yes.
and but I feel bad that people are going to feel like it's a nationalistic space race kind of situation, and so I feel like I just want
So the thing to remember here is the Chinese were locked out of the toy box. The United States won't allow a lot of technology developed here in the United States to be exported to China. And so we either abuse China to make our iPhones or we don't let them have our Xboxes. And because they are not allowed to be part of the International Space Station like most other nations in the world, they're like, okay, slow and steady wins the race. And they've been working systematically to develop the technologies they need to just go it alone. And slow and steady and careful and iterating on their designs, they're making amazing progress off on their corner, working by themselves because we said they can't play with us.
And now they're about to make the most, they're about to build their own international space station. They're about to invite the world to join them. They're about to put humans on the moon. The Chinese launched the most rockets last year.
Yeah.
So it wasn't SpaceX, it was the Chinese. So now, of course, they're dropping boosters into people's, houses. Um,
Mistakes were made.
no. They just do this. They just like they're one of their rocket launch facilities downrange is a place where people live, and they just evacuate every time they're going to launch rockets. And then if you get a rocket on your house, then they compensate you. Sorry, but progress marches ever forward. I guess is their attitude about this. So, yeah, uh,
Death and destruction marches forward.
yeah. Well, apparently, but again, the Chinese are working on their own version of reusable boosters. Ones are going to land on. Of course, they're going to nail this. So we're probably just a couple of years away from them having parity with SpaceX.
Yeah.
There you go. Arjona is saying that the Chinese had launches inland to protect them from attack a long time ago. That makes sense. Keep your rockets inland so that they can't be bombarded by ships
Well,
and things like that.
China and Japan were at war off and on for centuries.
Yeah.
And so there's still long-term cultural concern.
Jorn Albert says, can you discuss the current findings of the Anita experiment or make an episode? They have high confidence to have found the first particle outside the standard model, Sigma 7.
I know nothing
I have
about this.
not even heard about this. Can you put a link? I guess you can't put a link into the chat.
You should be able to.
Hint of weird particles from space. Oh, it's a balloon experiment. Cool. I don't think it's an episode, but we'll definitely
It's
take a look at it.
super pretty instrument.
Have a hanger with someone from Anita. That's a good call. Maybe I'll do that. John Suffield is noting regarding the Chinese lander on the far side of the moon on the TV news. Did anyone notice the Earth up in the sky, at least on the BBC? Basic faux pas by someone in the graphics department.
Yeah. That's kind of hilarious.
No,
They screwed up.
I haven't seen that. But yeah, the whole point of this is that it is on the far side of the moon, and they had to launch a spacecraft to be able to serve as a communications link to be able to even communicate with it. So, yeah. And then Ultima Thule, or
2014
MU69.
MU69.
Let me put a
It
picture
is
up of
a
that. If
red
any.
snowman.
Yeah.
Natalie Metzger did the best pareidolia realization of anyone I've seen. She noted that you can actually make out, if you use your imagination, two grumpy
Yeah,
faces in
I've
the
seen that.
objects.
Yeah.
It is,
I'll see if I can find that one. But
yeah,
here's the picture that we've got on this lovely Universe Today website. Um, so before, what it looked like. Oh, you can't see here. I'll share the view. So before, what it looked like, we just had this bowling pin or maybe peanut, and now it's clearly a snowman, and there's two grumpy faces. Especially, you can really see the grumpy face on this one.
yeah,
Yeah.
it's brilliant. So there are grumpy objects in the outer solar system. This is what's called a contact binary, and it is formed by two objects. You now are showing me twice. There we go. That's much less disturbing. Uh, it is formed by two different objects coming together and merging very, very slowly. And there was a little bit of debris thrown up in the process that formed a nice bright neck around the two objects. And statistically, these shouldn't be very common. And it's kind of awesome that New Horizons just happened to grab one as it flew past.
Yeah, it's interesting. I had heard that what you get is you get this, um, like you get the a cloud of material that's sort of forming together, and then it mostly merges into two blobs, and the blobs are going around each other as a sort of a binary
Yeah.
object, and they're slowly coming closer and closer to each other.
Tidal
But
forces are causing them to come together, just like Phobos is slowly attacking
right,
Mars.
but they are so small and so gravitationally weak that they just kiss as they just come
Yeah.
together. Just kind of softly crunch into each other, and nothing gets, they don't have enough mass to go into hydrostatic equilibrium, and so you just get this shape. And that apparently the neck is caused as well by material rolling downhill towards the other object. So this is the new downhill, and so objects will roll
Yeah.
down and sort of fatten up the neck of the object. So
Mika McKinnon did some amazing diagrams of this that are up on Twitter. She literally modeled these as spherical cows, and the sketches are adorable. And she does an excellent job explaining momentum
momentum. I gotta
because
check
they're
this.
spherical cows.
I gotta check this out. That is awesome. Now this is, I mean, the thing with this is that we are only a tiny fraction of the data has been sent back. We have to wait 20 more months for all of the pictures that were taken during this one quick little flyby to finally arrive back at Earth. So we are still, I mean, this is not the best picture that we're going to see. I'm surprised this is the only picture they've released so far. I don't know if one's out today, if something better is out today, but
Right now, they're downloading the spectral data.
oh,
And
for the scientists, yawn.
yeah, and one of the things about this that occurred to me is sure they have all the things they need to go to future objects as well, but they have to try and go to objects where the separation between encounter times is such that they can empty out their hard drive before they fill it up with the new object's data. So if like it's randomly discovered, oh my gosh, we are 4 months out from an amazing encounter with a hitherto undiscovered Kuiper belt object, they have to decide, do we pitch the data we currently have and don't have time to download, or do we just take a whole lot less data? And so the fact that space is mostly empty is really the one saving grace for this particular mission.
And they've got more fuel in the tank to be able to go to see something else, but right now they don't have any targets, and it's going to be
Yes.
difficult to make targets. It took the Hubble Space Telescope to find this one. So I know that Alan Stern is hopeful that they'll be able to
Yeah.
fly by something else at some point and New Horizons is ready to go to work, but we
Mark
don't.
Bowie, their photometrist, is one of the best out there.
And
Just
so,
flat out, he can find things that no one else can find. He also has the worst telescope luck. But yeah, it's if anyone can find them, I have faith that Mark can find them.
yeah, and that would be amazing to see another object in the Kuiper Belt. To Is it going to be another contact binary? Is it going to be something different, something weird? I mean, when you think about Pluto and Charon, right? You've got a binary object orbiting one another. A lot of the objects out there seem to have moons. Is there some kind of common interaction that happens that forms these things?
We don't know. And one of the things I haven't looked up, and I'm wondering if you have, is the direction that they're flying in one of the potential directions for Planet Nine.
Well, all directions are potential directions for Planet
But
Nine.
there, but there's certain places in the sky that they've already searched and eliminated it as not
Yeah,
currently being there.
I don't know, but even if it is like it would be incomprehensible luck if its future flight cone somehow includes Planet Nine. That would be,
Oh, I agree.
yeah,
I agree.
and its telescope is too small to help in any way.
Unless it were like amazingly lucky and won the space lottery.
Yeah, what I just said. Yeah, which is like if it somehow ends up that it's even marginally close to the future flight cone of New Horizons, that would be the gift of the century. Can you imagine?
It
It
really
really
is
would.
the like, what is it? Mega ball? I don't know the names of
Yeah,
the
yeah.
different lottery. It really is that kind of
I wonder what the
statistics.
odds would be, right? Somewhere within the, although they've actually searched the plane of the ecliptic pretty comprehensively and haven't seen it yet, so it's probably outside of the plane of the ecliptic. It's to some extent, and so for it to be somewhere out there would be in a way that they could actually make it line up would be just a mind bending
And
for
amazing.
yeah. Yes, yes, please. But then, I mean, if a Planet Nine is found, you can imagine probably Alan Stern and team thinking up a way to be able to go and visit it, and there'll
Except
be,
they'd call it Planet 10.
of course, yeah, no, there'll be a battle over who gets to name it and gets to land on it.
That would be like the greatest space drama to ever occur.
Have a race, and whoever gets there first gets to name it. Um, but but yeah, so you would put a uh, something like New Horizons, but you'd put it on top of, say, a Falcon Heavy and send it fast. Do a couple flybys, boom, get out there. Yeah, it would be great. Or on a starship. I still can't call them starships.
It's okay. I can't either.
No, we'll get there. Well, we're kind of reaching the end of our hour of Astronomy Cast. Thanks, everyone, for joining us this week. Another big reminder, a big thanks to our good friends at the Weekly
Oceanside
Space.
Photo and Telescope also.
Hold on. Weekly Space Hangout crew
Okay.
for
Yes.
organizing and being the wonderful community, and especially now as Google Plus is shutting down all of the Google Pluses and the communities and all of that stuff. Now is the time to migrate to some other platforms, such as the wonderful place that the Weekly Space Hangout crew has done. So go to wshcrew.space and they will hook you up. What did OPT
It
do?
is true. Oh, just in general, for being super helpful the past week, providing telescope support. Um, yeah, sorry. Random thanks are
Thanks to
just going to keep
OPT.
happening for a while.
Well, speaking of, OPT has a new podcast with Tony
Yes,
Darnell.
they're working
And
with Tony Dell.
yeah,
Yeah.
yeah, you should totally check that out. So if you want to add another space-based podcast to your list, go and check out the new, they call it Space Junk. So check that out. And we'll give them a better boost in next episode. All right, remind me to do
Yeah.
that. Okay, well, thanks everyone. We'll see you all next week.